Okay, we're back with talking about the lab that we would have done if we were together today. Actually, a really great lab to miss if we have to miss one. So basically the point was somebody was going to stand in one spot and another person would run. The first trial, if I can remember right, you would have the person running with their arm outstretched like this and a stuffed animal or something. We usually use the red pig Beanie Baby called the physics pig, cleverly enough. And you run, and then when you get to the person who's standing still, the runner would let go of the Beanie Pig and continue running at the same pace. So we're trying to get a runner going at constant velocity. What would happen, where would the pig land in relation to the runner? Where would the pig land in relation to the stationary person? Well, if the runner lets go of the pig and continues to run at the same velocity, then does the pig have any velocity in the x direction? Well, yes, the pig and the runner should be going the same speed in the x direction. When the pig is just dropped, it still continues to go in the x direction. Then it also starts to move in the y direction due to gravity. So the pig has the acceleration equal to the runner in the x direction. It has acceleration due to gravity, so velocity of the runner here. Initial velocity is 0 in the y direction. Final velocity is, well, we could calculate that based on how far it falls from the person's arm to the floor, and multiply it by gravity, of course. Just like we did using the Lab 4.2 when the car fell off the table, you would calculate it the same way. Anyhow, we would expect that the runner and the pig would continue to move at the same speed, and the pig would hit the ground right next to the runner, and it would be somewhat behind the person who was stationary. Then the next trial would be the stationary person would stand holding the pig on their hand, standing still. The runner would run past and barely tip the pig off the person's hand. In that case, we would expect that they're not trying to impart a lot of velocity in the x direction, so hopefully we get very, very little in the x direction, hopefully negligible velocity in the x direction, in fact, so that the pig would just tip right off the person's hand, fall straight down, and only have velocity in the y direction. In this case, we would expect the pig to land right at the feet of the stationary person while the runner goes on by. The third trial is the runner would try to knock the pig off as they run by with a large amount of force, trying to equal the velocity in the x direction for the pig that the runner actually has. So we would once again expect the pig to land much closer to where the runner is still running at that constant velocity than where the stationary person is standing still. Just to show a little bit about friction, you can read that in the book. That's, I think, Lab 5.2. Maybe not the most fascinating of labs, but 5.2, Lab 5.2 that we'll do in class next week is very interesting. So might want to give it a read through before class also, just because it's kind of complicated. I'll walk you through it. Once you break it down, it's very easy to understand, but it'll help if you read it through once, just because it seems more complicated than it actually is, which you'll find to be the case in pretty much every lab we do from now on. Make sure you remember vector quantity for force must have a magnitude, unit, and direction. I have a note to remind you of that on every page that I pick up, apparently. So we're going to do, looks like 8 review questions this week. Ooh, forgot to start my stopwatch again. Okay, so number 1, state Newton's 3 laws in your own words. I hope you've written these down. Pause if you don't have an answer and make sure you know them. And then unpause. And first, Newton's first law, an object in motion will remain in motion. Likewise, an object at rest will remain at rest unless they are acted upon by an outside force. Newton's second law, best described by the sum of forces is equal to mass times acceleration. and there's definitely like a long wordy thing, but F equals ma will do just fine. Number 3, Newton's third law, for every force there's an equal and opposite force. One force directed at something, the other force directed at the thing directing the first force. So, number 2, why will friction always be present when two surfaces touch each other? Once again, make sure you've written something. But remember, at the atomic level, there are bumps and grooves. They, just like a car would crash into a mountain unless it could go up over it, these little bumps and grooves cause stopping, and they, are a force that you have to overcome to push on past those little things. Also, there are electrostatic interactions that have to be overcome to get two things to move apart, slide on past each other. So the more friction is greater when the two things are at rest in relation to each other, and it takes a little less force to overcome friction as two things are in motion, sliding past each other already. And we'll talk a lot more about that in a little bit. Maybe not today. Number 3, a man is riding a horse at a quick gallop, and suddenly the horse stops dead in its tracks. When this happens, the rider flies out of the saddle and lands on the ground. Which way is the rider going to go? So we've got horse going this way, rider, of course, on top of the guy going that way also. Red and orange are not going to do for this. So rider on top, horse on there. Horse stops. Where does rider do? Well, according to Newton's first law, an object in motion will remain in motion. So the horse uses force to stop itself. The rider, not so lucky. There's only a certain amount of friction between the rider's seat and the horse's saddle. Clearly not enough to stop him in this case, so he's going to continue to go in the direction that he was going due to Newton's first law. So he'll go forward over the front of the horse, continuing right in the direction he was going, because force is a vector, which is unfortunate for that guy. Number 4, a student applies the same force to two objects. If the first is 1,000 times more massive than the second, which one will accelerate more quickly and how much more quickly? So, when you have a question like this that asks you to look at an equation and decide what will happen if you change one of the numbers, you must write the equation on your test. I'm not kidding, you really need to. I've seen people just tell me an answer, not really prove it. These are going to get much more complicated as the year goes on, so you really need to start showing your stuff. Okay, so we have a force, we have a mass, and we have an acceleration. Clearly we're talking about F equals ma, Newton's second law's equation. Okay, so it says a student applies the same force to two objects. So the first force and the second force are equal, right? The first is 1,000 times more massive, so mass 1 equals 1,000 times mass 2. The first is 1,000 times more massive than the second. Which accelerates more quickly and how much more quickly? So we look at this, our forces are equal, our masses are different, so we're going to change, increase in the mass, 1,000 times, and how much more quickly will it accelerate? So if forces are equal, we change the mass. What will happen to acceleration? Well, acceleration clearly for the more massive one, so the more massive one is the first. Acceleration for the more massive one is going to be much slower because when mass goes up, right, then if force is constant, acceleration is going to go down because they are inversely related. You can see if mass goes up, acceleration has to go down. Mass 1 here is much greater, so acceleration would be much less. So which one is going to accelerate more quickly? Well, mass 2. So you want to show your equation, you want to show this inverse relationship. As mass goes up, acceleration will go down. So that's the key right there. Let's see. Number 5. Which of the following is a legitimate force unit? So here you see pounds, that's the English force unit. Slug, well that's the English mass unit, so no, that's not a force unit. Kilogram meter per second, well, we know force units have to have a mass times a distance divided by a times squared. This doesn't have that. So kilogram meter per second is not a force unit. And then the slug mile per hour squared, well, that has a mass times a distance divided by a time squared. So that is indeed a force unit. Not a very common one, but it is. So those two, pounds, and then this last one, slug mile per hour squared. Both valid force units. You must have mass times distance divided by time squared. Number 6, a physics student measures an object and writes down a value of 13.1 newtons. What was the student measuring, the mass or the weight? And newtons tells us what? Weight. The student's measuring weight if they're using newtons as their unit. Number 7, a physicist uses a same scale, so he takes a mass scale, to measure the mass of an object in 2 different locations. Death Valley, which of course is well below sea level, and the top of Mount Everest, which is the highest point above sea level. Is the measurement going to be accurate in both locations? Why or why not? So remember precision and accuracy. Precision tells about the tool you're using. How many significant figures can it give you? Accuracy tells, does it tell the truth? Well, it says he's trying to measure mass. So will mass change based on the location? Will the mass of an object change? No, mass is not the kind of quantity that changes. Something is made of what it's made of, and that mass does not change based on where it is. So no. The measurement should be the same because mass is the same. Probably a scale is built to measure weight. You can't really measure mass. You can't measure the stuff. So what they're doing when they build a scale is they're building in a force measurer, and then they're drawing the scale like based on a division of that force by the acceleration due to gravity. And so they're really measuring force and then drawing this scale to account for gravity. But gravity would change somewhat based on the altitude from Death Valley to the top of Everest. So probably what the scale is going to report is going to be a slightly different weight converted to mass, telling you that the mass has changed, when in effect the object's mass will not change no matter where it is. So I would say that scale is not going to work out very well. And number 8, what is a normal force and why is it important in physics? Well, we get our box. We say, right, the box has a weight which pushes down on the surface the box is on, and the surface the box is on then will, according to Newton's third law, exert an equal and opposite force, which is the normal force, F sub n. So the normal force is always going to be perpendicular to the surface here at a 90-degree angle there. And so it's a force resulting from contact of 2 bodies perpendicular to the surface of contact. So all the review questions are done. Hopefully I haven't run over, and I'll turn it off and see you in a minute.